Welcome to AI Paper Slop. So, for the last few years, multimodal foundation models basically took this massive shortcut, right? They just consumed the entire internet to learn how to see and speak.
Yeah, text, images, basically all the easy data.
Exactly. But if you're building an embodied AI agent, robot actually operating in the physical world, it really can't take that shortcut. I mean, physical reality doesn't output discrete text tokens.
No, it definitely doesn't.
These models need data that tightly couples visual observations with, well, physical states and, crucially, executable actions. So today we are diving into a massive July 2026 collaboration, and this spans researchers from PKU, NTU, HKUS, and US, UC Berkeley, a bunch of others.
A huge joint effort.
Yeah, massive. The paper is titled Data Pyramid for Embodied Manipulation. And basically, the authors map out the whole embodied data ecosystem as this 5-tier pyramid, which is organized around this really fundamental tension between scalability and robot alignment. By systematically mixing these 5 tiers, so you've got real robot data, UMI-style data, human video, simulation, and general web data researchers are trying to power the next generation of vision language action models and world action models.
Yeah, exactly. Because if you are an ML engineer working in robotics right now, you already know the neural architecture is just, well, it's no longer the main bottleneck.
Right.
We have the transformer variants mapped out. The diffusion policies are scaling efficiently. The real bottleneck holding everything back is the data recipe. So this paper systematically unpacks how action-labeled data actually grounds your models in physical interaction, while massive amounts of action-unlabeled data preserve the latent dynamics.
Right, because training an LLM or standard VLM is essentially, working with infinite, perfectly discrete data. You scrape text, you scrape images, and the model learns to map language to visual concepts.
But observing a task is just fundamentally different from executing it.
Exactly, like a VLM watching a video of someone making coffee, it learns the semantic sequence. Grab the mug, place it under the machine, press the button.
Yeah, but it learns absolutely nothing about the joint torques required to actually lift that heavy ceramic mug, right?
Yeah.
Or the tactile feedback of a plastic handle slipping in its grip.
Oh, for sure.
That is the execution gap. And the authors organize the data we can realistically collect to bridge this gap along 2 primary axes. On the horizontal axis, you have scalability. Like, how easy is it to acquire millions of hours of this specific data?
Right.
And then on the vertical axis, you have robot alignment, meaning how closely does this data match the actual physical kinematics, the control frequencies, and the sensor layouts of your specific target robot?
And those 2 axes are just in direct conflict. I mean, you cannot easily scale perfectly aligned data.
No, not at all.
So to evaluate where a data set falls on that spectrum, they use 4 complementary dimensions. Quality, which is the task relevance, diversity, so coverage across different out-of-distribution states, reusability, how easily you can transfer it to a totally different embodiment.
And physical fidelity.
Right, how closely the data respects real-world physics. I actually like to think of this like a nutritional pyramid for the ML crowd.
Oh, okay.
The general vision language data, that's the cheap, abundant carbs at the base, but real robot data is the incredibly expensive, really hard-to-source protein at the apex.
I love that analogy.
Right, you need both to build a healthy model, but, you consume them in drastically different quantities.
Yeah, and looking at that protein tier 1, the real robot data, this gives you direct robot control signals, perfectly coupled with physical world interactions. It is the absolute gold standard for executable control.
But it's so hard to get.
Oh, it's terrible. Collecting it through standard human teleoperation is just incredibly painful. You're dealing with network latency, these awkward mappings between a human hand and a rigid robotic joint.
And it invariably results in these jittery, totally suboptimal trajectories. Right?
Always. So the paper actually advocates moving away from that and heavily adopting integrated leader-follower teleoperation, which instead of a clunky joystick or VR controller, you use a lightweight leader arm that kinematically matches the heavier follower robot.
Oh, so it physically mirrors the hardware, but without the mass.
Exactly. The human operator gets a highly fluid, intuitive experience. It preserves the fine-grained trajectories while capturing that direct physical interaction feedback.
And to squeeze even more value out of those expensive real robot trajectories, the authors push for aggressive use of AI-generated content, or AIGC, to synthesize and augment scenes.
Wait, so like taking one trajectory and multiplying it?
Yeah, exactly. You take one single trajectory of a robot picking up a block, and you use generative models like Stable Diffusion to dynamically alter the background.
Oh, wow. So you change the lighting from morning to night,
Or artificially add visual clutter to the table, yeah. You artificially expand the environmental distribution without the exorbitant hardware costs of physically moving the robot to a new room.
That's super smart. But we can't just collect happy path demonstrations, though.
No, definitely not. The paper stresses the critical need for policy rollouts. You let a partially trained agent explore the physical environment to induce its own state distribution.
Because it will inevitably make mistakes.
Exactly. So the human operator monitors this in real time, steps in the exact moment the robot fails, corrects the mistake, and you record that specific recovery trajectory.
And that directly addresses covariate shift in standard behavioral cloning. I mean, if a model only ever sees perfect, ideal execution, the moment it drifts a millimeter off that ideal trajectory during deployment,
It's completely lost.
yeah, it encounters a state space it has literally never seen before. It has no idea how to recover, and those spatial errors just compound until you get a catastrophic failure. Policy rollouts actively teach the model the boundaries of the state space and the precise control logic needed to navigate back from the brink of failure.
Which is so crucial. But here's my question. If real robot data is the absolute gold standard for executable control, why not just build massive robot farms? Like we build GPU clusters, why not treat physical hardware the same way and just run tier 1 collection 24/7?
I mean, a lot of companies are trying to brute force it exactly like that.
Right.
But it's an absolute logistical nightmare. You have continuous hardware degradation, motors are burning out.
Sensors constantly drifting out of calibration, I bet.
Exactly. The physical world simply does not scale like a server rack. And beyond the maintenance nightmare, a robot farm completely lacks environmental diversity.
Oh, because 100 robots operating in one warehouse only learn the physics and the lighting of that specific warehouse.
Right. To get true diversity, you would need robot farms in thousands of dynamically changing environments, which is economically completely unfeasible.
Which naturally forces us off the robot arm entirely. To get that environmental diversity, real home kitchens, messy factories, office spaces, we move to tier 2, which is UMI-style data, or Universal Manipulation Interface.
Right, where you untether the camera and the gripper from the heavy robotic base.
Yeah, a human operator just holds a specialized portable rig with a camera and a robotic gripper attached, walking around interacting with everyday objects. You capture explicit end effector supervision entirely in the wild.
You gain massive environmental diversity, but it introduces a severe computational penalty.
The calibration.
Oh, the complex calibration. You're capturing the spatial trajectory of the end effector in 3D space. To execute that trajectory on a real robot arm later, you have to solve the inverse kinematics.
So mathematically calculating the exact joint angles required to map that 3D spatial trajectory back onto a 7 degree of freedom robotic structure.
It's incredibly tough. You face continuous calibration drift, severe retargeting challenges, and just the stark reality that a human wrist navigating 3D space has fundamentally different constraints and singularity points than a robotic joint.
And that computational penalty is exactly why we rely so heavily on the base of the pyramid for scale. Tier 5 is general vision language data, internet scale text and images.
Highest scalability possible, but absolutely zero robot action alignment.
Exactly. It builds the embodied brain for semantic reasoning, teaching the model what a microwave actually is. But the physical reasoning really begins at tier 4, which is simulation data.
Yeah, simulation allows for the parallel, hyper-accelerated generation of robot-oriented experience.
Yeah.
And its superpower is privileged information.
Right.
In the physical world, calculating the exact center of mass, the friction coefficient, or the precise 3D bounding box of a novel object is incredibly difficult. But in a physics simulator like Isaac Jim or MuJoCo,
You have instantaneous access to the exact ground truth state of every molecule in that environment.
exactly. You train a teacher policy using reinforcement learning on that perfect information, and then distill that capability down into a vision-based student policy.
And the paper also tracks this massive shift toward using world models as simulators. So instead of building rigid, polygon-based 3D environments, researchers are using generative video models.
You feed the model an image of a physical scene and an action prompt, and it just generates the next physical frame of video.
Right. The generative model is acting as a differentiable physics engine, learned entirely from massive data ingestion rather than hard-coded kinematic equations.
Yeah, but whether you use a traditional physics engine or a generative world model, simulation is haunted by the sim-to-real gap. The simulator will never perfectly capture the complex dynamics of a soft sponge deforming,
Or the variable glare of sunlight blinding an optical sensor? Actually, there's a contradiction here that always bothers me. We train models in simulation because the real world is too messy and expensive.
Right.
But then, to make the simulation useful and cross that sim-to-real gap, we use domain randomization. We artificially inject the messiness back in.
Randomizing lighting, textures, camera angles, scrambling the physics parameters. Yeah.
Aren't we just running in circles? Like, we leave the real world to escape the mess just to code the mess back in.
I mean, it definitely looks like a paradox, but it's actually a highly efficient compression of the problem space. By injecting that artificial messiness, we force the neural network to learn representations that are invariant to visual noise.
Oh, so simulation data builds a massive prior for physical reasoning.
Exactly. It teaches the model the fundamental laws of kinematics and control logic. When you finally deploy that model in the real world, you only need a tiny fraction of that expensive Tier 1 real robot data to fine-tune it.
Because the model already knows how to move its arm to a spatial coordinate, the real-world data just teaches it the final millimeter-level tactile adjustments.
Yeah, so we have our massive prior at the base and our executable control at the apex. Bridging them is Tier 3 egocentric and exocentric data.
Right, the messy middle. This is video data of humans doing things. VR headset footage, wearable cameras, YouTube cooking tutorials.
And it captures incredibly diverse human activities and, most importantly, long-horizon task structures.
It shows the model, the sequential logic of a task, like how making a meal requires fetching ingredients, prepping tools, cooking, and cleaning in a very specific order.
But the major bottleneck they identify here is the human-to-robot embodiment gap. A human hand is this insane biomechanical marvel.
Right. When a human folds a shirt, they're using over 20 degrees of freedom, soft tissue compliance, dense tactile arrays across their skin.
And if you try to map that visual data directly onto a standard robot with a two-finger parallel jaw gripper, the mathematical mapping just breaks down entirely. The robot physically cannot replicate the complex grip strategy the human used.
So how do we actually use this data if the physical actions don't map?
Well, the field is developing a growing tolerance for noisy, misaligned trajectories, provided the scale of the data is just large enough. We aren't trying to force the model to replicate the human hand's exact joint angles.
Oh, we're forcing the model to extract the affordances of the objects and the state transitions of the environment.
Exactly. If a model watches 10,000 videos of humans opening different doors, it learns the universal concept of a hinge and a handle, regardless of the specific fingers used.
Which dictates how we map this 5-tier pyramid onto the actual neural architectures being built today. You know, vision language action models or VLAs and world action models. Whams.
And the foundational takeaway from the paper's analysis here is the distinct split between action-unlabeled and action-labeled data.
Action-unlabeled data being the Tier 3 human videos and Tier 5 general web data.
Right. That data preserves general capabilities and teaches the model latent dynamics. It internally models gravity, object permanence, collision, without ever seeing a single motor torque value.
It basically builds the mental model of how the world operates. But to actually interact with that world, you need the action-labeled data, Tiers 1, 2, and 4.
Real robots, UMI, and simulation. That labeled data acts as the translator, converting the model's abstract understanding of physics into a concrete motor command.
So if I'm an ML engineer right now training a VLA, is there a golden ratio? Like 80% simulation data, 20% real robot data. They always want a clean formula.
Honestly, the paper clarifies that the optimal recipe is still completely unresolved. We haven't perfectly isolated the mathematical contribution of each individual source at scale.
Interesting.
Yeah, what's really fascinating for researchers trying to build generalist agents is that robot-only models, trained exclusively on Tier 1 data, still achieve surprisingly strong performance in narrow, domain-specific tasks.
So we don't necessarily have to have everything everywhere all at once.
Right. The massive multimodal training recipes are the theoretical path to general-purpose robots, but the exact mixing weights remain a highly active area of empirical discovery.
Well, the field is clearly far from solved. The authors close out the paper by outlining 6 open challenges for the future of embodied AI. And I feel like this is exactly where listeners should be directing their research, compute, and engineering cycles.
Totally. Challenge 1 is building large-scale tactile data sets. Vision is great for navigation and approach, but the moment a robot gripper actually closes on an object, the camera view is usually heavily occluded.
You lose your primary sensory input right at the critical moment of physical interaction.
Exactly. We need data that captures touch, slip, microvibrations, and force feedback. Integrating dense, high-resolution tactile sensors like gel site sensors that measure elastomeric deformation into robotic fingertips without destroying their physical durability is just a massive hardware and data processing challenge.
Then challenge 2 is collecting failure and recovery data, which we touched on earlier with policy rollouts.
Right.
And I have to say, this is so unnatural for traditional supervised learning. Normally, if you have a data set and half of it is bad outputs, you filter the bad data out, right?
To improve the signal-to-noise ratio, yeah.
But in robotics, that bad data, the failure state, is exactly the signal you need to teach robustness. If you throw it out, your robot breaks the first time it encounters a slightly heavier coffee mug.
Or a floor with an unexpected friction coefficient. Challenge 3 is developing scalable data collection pipelines. We need entirely new hardware and software stacks that make gathering Tier 1 and Tier 2 data drastically cheaper.
Rigs that are self-calibrating, batteries that last significantly longer.
And data storage solutions that seamlessly upload physical trajectories to the cloud without requiring manual engineering intervention at literally every step.
Challenge 4 is aligning actions across different robot embodiments. Say you spend millions of dollars training a highly capable policy on a 7-degree of freedom Franca arm. How do you zero-shot transfer that policy to an industrial UR5 arm with entirely different kinematics?
Without starting from scratch, exactly. Researchers are exploring morphological translation layers in shared latent spaces, but a universal mathematical translator for robot hardware just doesn't exist yet.
Challenge 5 focuses on leveraging that egocentric human data for true dexterous manipulation. As we move away from simple parallel jaw grippers and start deploying complex, multi-fingered robotic hands, the human-to-robot embodiment gap shrinks slightly.
But the algorithmic complexity completely explodes. We need better mathematical models to map a human's 5 fingers onto a robot's 5 fingers directly from 2D video, dealing with heavy self-occlusion.
And finally, Challenge 6 is designing principled data recipes for robot learning. We really need to move away from mixing datasets by intuition.
Yeah, the LM world has the chinchilla scaling laws, dictating exactly how to balance compute and dataset size to hit the compute optimal frontier. Robotics desperately needs its own rigorous scaling laws.
We need to know exactly how many tokens of human video data mathematically equal 1 token of real robot physical interaction.
Exactly. Looking across these 6 challenges, the landscape of robotics is clearly transitioning from a period of rapid architectural exploration to a period of rigorous data-centric engineering. The physical capabilities of tomorrow's agents are entirely bottlenecked by how creatively and efficiently we can source, align, and mathematically mix these 5 tiers today.
So we've covered the pyramid, the scaling tensions, and the data recipes powering the next generation of embodied agents. So what does this all mean for the horizon of our field?
I'll leave you with a final provocative thought to mull over. We're currently pouring immense resources into bridging that human-to-robot embodiment gap. But as we push towards highly advanced world action models, models that learn the latent dynamics of the universe from massive amounts of unlabeled human video, will that embodiment gap eventually just become irrelevant?
Wait, really? How so?
Well, think about it. If a world model understands the physical rules of reality perfectly, could it zero-shot translate the visual of a human hand cracking an egg into the exact, precise joint torques needed for a 2-fingered robot claw to achieve the exact same state change?
Completely bypassing the top of our data pyramid.
Exactly. If the model's internal physics engine becomes computationally strong enough, it might just bypass the apex altogether, rendering expensive real robot data completely obsolete.
Now that is a wild future to design for. You can find a specific data recipes and the full breakdown in the Data Pyramid for Embodied Manipulation paper. Take these frameworks, look at the composition of your own training runs, and start rethinking your data pipeline. Until next time on AI Paper Slop, keep building.